The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Our final talk today is going to be given by Paul Tennis. Paul is with the Portland Cement Association, but he's not one of us Skokyites. His office, I guess, is in Fort Mill, South Carolina. Paul has been involved, I think, in seeing a lot of the work, seeing the industry's response to some of the concerns about the use of potassium acetate, and is going to provide us an overview of agency and industry-sponsored research into the effects of potassium acetate on concrete durability. So thank you very much, Paul.
Thank you. All right, well, good afternoon. I'm glad I'm standing between everybody and lunch. If they get a chance to get lunch, I will try to go quickly. As Tom mentioned, this is sort of an overview of several different research projects, and so I've got maybe two challenges immediately before me. One, I didn't do the work, so a lot of the details and what I choose from the hundreds of pages of research reports, which is the second challenge, trying to condense multiple 100-page reports down into a 20-minute presentation is another challenge. But I do hope to provide an overview of what those projects concluded, especially because we work together as a cohesive team, or ideally as a cohesive team to get here. So as a brief history, I think it may be familiar with this, and Thano started a good summary of this. There was premature distress noted in airfield pavements in the late 1990s and early 2000s. It looked like ASR map-like cracking. Some surface scaling was also evident. It appeared to be related to potassium acetate exposure, where this anti-icer deicer was being used. Potassium acetate is a particularly effective anti-icer and deicer. I think Larry or Doug might have mentioned that some of the calcium magnesium acetates can go down to 30 and 40 degrees below zero. I think potassium acetate actually goes to something like 60 below zero, and it's still effective. And also, in keeping with the theme of responsibility for our convention here, potassium acetate has another advantage in that it breaks down in the environment to relatively benign species, so it's environmentally friendly. And that means if you're de-icing airport runways, you don't have to build collection facilities and other structures to deal with it. So the FAA, airport maintenance staff, liked potassium acetate. They still like it, and they wanted to keep using it, and so it was sort of incumbent upon the concrete industry to look at this potential deterioration issue and come up with a concrete-based solution. And in response to the apparent problem, in 2003, FAA and IPRF started some initial work, laboratory work, that seemed to confirm that potassium acetate would indeed at least exacerbate ASR where reactive aggregates were present, and in some cases cause non-reactive aggregates to fail as well. Interim protocols to try to deal with this potential issue were issued by FAA in 2005, and a working group was formed shortly thereafter. And this group was informally organized by PCA, and John Melander, my co-author here, was instrumental in putting this together. We worked in cooperation with the American Concrete Paving Association, Innovative Pavement Research Foundation, IPRF, and FAA and FHWA were involved as well. We wanted to establish consensus on the scope of effort involved in researching this problem, develop shared goals to identify what questions needed to be focused on. It also provided an information sharing forum so that these independently funded research projects could come together while they were ongoing, rather than trying to wait, maybe do these kinds of research reports sequentially. We thought by meeting while the projects were going on, interim results could be shared and some changes could be made to research programs to accommodate those. And the whole thing was geared towards getting the answer much more quickly. These were the most of the participants in the working group. I might have missed a couple of individuals, but you'll recognize a lot of names. I mentioned the agencies involved. Many of the researchers are here in the room as well. And I'll talk about who did what as I go through the presentation. And of course, many of these are members of ACI 201 and other ACI committees. So I hinted at this already. The goals of the working group were to coordinate the research effectively and efficiently to try to develop solutions to this potassium acetate issue. We wanted to understand what the deterioration mechanisms were, apply whatever analytical tools we could develop or could pre-existing tools. If we could develop rapid test methods that correlated with field performance, that was a key goal as well. And we also wanted to verify and predict long-term performance. And our overarching goal was really to develop practical specifications that would ensure concrete durability in the field. I think Thano covered this early indications as well, but I'll just summarize them quickly. The early testing was based on modified C1260 and C1293 laboratory tests. Potassium acetate was demonstrated to accelerate ASR. Enough Class F fly ash or enough slag could be used to mitigate that issue, but Class C fly ash did not seem to help out. And then concrete, of course, with non-reactive aggregates could also be deteriorated. Early field results indicated that ASR did not appear to be limited to the surface of the pavements that were involved or be limited to potassium acetate exposure. Core profiling did indicate that there was limited potassium acetate penetration into the concretes, and as Thano noted, there was some elevation of arcanite, potassium sulfate, near the surface of some of the pavements. And then there was evidence of other construction issues, other materials issues, poor consolidation, marginal air void systems, and then traditional ASR. So several mechanisms were identified early on in the working group's meetings, and that was what were the mechanisms for exacerbating ASR, what might be causing surface deterioration and paste alteration, what kind of deleterious interactions with SCMs might be going on, particularly with Class C fly ash, and then could potassium acetate simply be causing an exacerbation of freeze-thaw resistance or freeze-thaw deterioration by some mechanism. And then we also noted, of course, that more than one of these mechanisms could be going on at the same time. So I've got 4 projects that I'll cover. I'll skip the one that Thano covered in the interest of time. But the first project was done at the University of Toronto, and I think actually Doug might have just left. But Doug Hooton and Sonia Gahar-Khosravi were the investigators here. And the primary goal of this project was to look at the effects of potassium acetate on ASR resistance, freeze-thaw resistance, deicer salt scaling, and also they were looking at actual penetration profiles of potassium acetate into concretes. And all this was laboratory work going on. They did a wide range of testing, the traditional ASR testing modified with potassium acetate as a exposure solution, freeze-thaw testing, salt scaling testing, and absorption testing, the C1585, X-ray diffraction, petrography. They used different solution concentrations of 3 molar and 6 molar potassium acetate, and then they used a variety of materials, 2 different cements, 3 different SCMs, and 4 different aggregates. So a very large matrix of research going on. And, again, out of a couple hundred-page master's thesis, just as an example, you can see that they looked at the potassium to sodium molar ratio as they profiled through a concrete specimen. In this case, a reactive aggregate was used, and over the course of a year, there was some potassium acetate infiltrating the concrete in the laboratory. Now, some of the conclusions from this work were that potassium acetate can increase ASR-related expansion, but the supplementary cementing materials could mitigate that expansion. Potassium acetate did penetrate the laboratory specimens over time, and that in the freeze-thaw testing, and salt scaling testing, the air-entrained concretes performed very well. The non-air-entrained concretes were actually internally damaged, even though there was no surface damage, and it's likely because in these solutions there was no actual freezing at the surface. Even when the concrete got very cold, the surface didn't freeze, but the interior did. And then they also did some testing on the aggregates themselves, and they found that some of the aggregates they used, when they exposed them to potassium acetate, they release sodium into the solution. So some indication that that might have been have an impact on the ASR resistance if sodium's being generated through some kind of reaction, and potassium is also adding alkalis. The ASR reaction could be more damaging. Another project was done at Michigan Tech. Larry Sutter, Jerry Anzalone, and Carl Peterson were primary investigators, and they focused on laboratory work on, again, focusing on basic mechanisms, but looking at solubility and dissolution rates. And so they used some mortar bar testing, but a good portion of their work was done with a modified C289 test. That's the quick chemical test. It's sort of a ASR test on aggregate to determine how reactive it might be, and it's fallen out of favor, I think, because of a lot of false positives. But in this case, they were using it to look at solubility of aggregates, and they used two different aggregates and a borosilicate glass as a monoaggregate. And they were looking at the solubility of those aggregates when exposed to concentrated solutions of potassium acetate, as well as, you can see here, sodium hydroxide, potassium hydroxide, calcium hydroxide, and all at various concentrations. So they're looking at trying to get background information to feed into potential mechanisms. And some of the conclusions they had were that expansion seems to be occurring in their mortar bar testing when the silica dissolution rate exceeds the diffusion rate of hydroxyl ions. So if silica is dissolving faster than hydroxyls can diffuse away from the reactive sites, you get reaction products forming. They fill in the pore space and they create expansion. If some of the products can move away from the reaction sites, then they either don't form, the hydration products don't form, or they're not expansive. And what they found was that the potassium acetate effect was to increase both the dissolution rate of the silica as well as the nature of the hydration products. So some of them were more mobile and some of them were less mobile, and so the expansion itself really depended on both the aggregate mineralogy as well as the particular solution chemistry they were looking at. And then again, when looking at a large number of mortar bars and a large number of different solutions, they noted paste densification was a common effect in potassium acetate solution. So it's the same aggregate type here in one normal sodium hydroxide and then one normal sodium hydroxide. In addition to potassium acetate, the darker paste here is indicative of densification due to this hydration products forming. Now, this was Mike Thomas and Sean Heyman's project. It was also later collaborated with the University of Texas, and Thano covered this in good detail, so I'll skip through here. But I think a primary contribution of this work to the working group exercise was that these were controlled field studies, and they were applying potassium acetate to known materials, known mixed designs, and so that provided some useful data. And then the IPRF project 05-7 was performed by Prasad Rangaraju and his students Chandra Balachandran and Dave Wingard, as well as Jan Oleg at Purdue and a team of researchers there were providing support to Prasad. This was a forensic investigation of airport pavements. So they cored 16 pavements at 8 different airports, the majority of which were exposed to potassium acetate. I think all of them were exposed to potassium acetate, and most of them were suffering damage. There was a small set that weren't suffering any damage, even though they were exposed, and they wanted to see what was done right in those concretes. So as a traditional forensic investigation, they looked at materials information they could collect from construction records and people's memories, as well as pavement service information, where they could figure out how much potassium acetate was applied over time, as well as what other deicers might have been used. They did petrographic and microstructural analysis. They did a significant amount of work looking at depth of penetration of potassium acetate, hard and air void analyses, pulse velocity measurements, and freeze-thaw testing of some of the cores exposed to potassium acetate in laboratory after they're brought in from the field. The conclusions from this forensic investigation really sort of provided an answer to the perceived problem. In every case where they were coring pavements from distressed pavements, they found other issues that were responsible for the deterioration. Most significantly, they found ASR that was not sufficiently mitigated. So there was Class C fly ash used at low dosages, or there was Class F fly ash used at insufficient dosages, no SEMs used. In other cases, other airports, there was some alkali carbonate reaction found. Drying shrinkage problems, freeze-thaw deterioration with marginal air void contents, poor consolidation. So there was no case where potassium acetate could really be pointed at as a field cause of the dissolution. And I mentioned the penetration, and I think this was consistent with Thano. Most of these pavements were in the order of 15 to 20 years old, and the deepest penetration of potassium acetate in the field was about 15 millimeters. So the common conclusions of the working group, they met after several years of ongoing research, and in the laboratory there was general agreement that potassium acetate can cause or accelerate deterioration, either due to ASR or even without susceptible aggregates being involved. And it was noted that the accelerated testing uses high concentrations, they use elevated temperatures to accelerate the effects, and they have a high continuous supply of alkalis, and that may be the reason that they don't necessarily relate to field performance. And then that was the other conclusion, was these lab tests don't appear to be correlating with field behavior. In the field, potassium acetate is widely used as a deicer, but has not been shown to cause observed distress. The penetration of potassium acetate into those concretes was very limited, even over a 15 to 20 year time frame. But it was noted that since we only have 15 to 20 years worth of data, we need to continue to monitor these pavements in the field because the laboratory testing does indicate a potential for long-term deterioration. So that was a recommendation. It's also noted that specifications have been improved since many of these pavements were in place. I'll just say that there's more stringent and more accurate test methods that are involved now than there were 20 years ago, and more better understanding of what appropriate mitigation protocols are needed. And so it's anticipated that ongoing future pavement construction for airports will not necessarily have some of the deterioration from some of the causes that were noted in the forensic investigation. And then I'll just I'll sort of end here with a plug for the working group concept. In this case, potassium acetate was not really a field problem that we thought it was at the beginning of some of these research projects. But by working together to share interim results in a frank and open discussion forum, and note where some preliminary results weren't what we were expecting, or that some lab problems occurred that needed to be replicated. And by looking at field investigations, controlled field testing, and laboratory evaluations all simultaneously, rather than possibly separately or sequentially, I think we did essentially answer the questions quicker than we might have otherwise done. And so I'd probably just put in a plug for that kind of concept in the future. Different funding agencies and different research teams working together to try to get to technical solutions faster. And that's basically, I think
Are there any questions for Paul? Yes, please, and speak into the microphone.
What sort is cement tried?
that was actually a suggestion for future work, but it was also in one of the work at the University of New Brunswick. That was one of the goals of the program, and they didn't get to that part of the research. So I don't know that surface sealants were ever tried in a controlled study.
Is there any other questions? Thank you, Paul.